Ben, and what I'm going to talk to you today is sort of an attempt, at least, at an interdisciplinary approach to an old problem in seismology, which is classifying earthquake data. As an aside, you could use the techniques that we'll talk about today to classify any data that's sort of on the domain of a sphere. So any sort of data on the surface of a sphere, you could use these techniques, and particularly any problems that are based in sort of wave mechanics or wave phenomena. So I sort of I came to working in earth science sort of commercially from a background of theoretical physics and quant finance. So coming into this field, I tend to look at problems sort of more from a machine learning perspective sort of to start with, right? And I think, like a lot of us here, it's a great opportunity in using the SciPy Python code stack to find new solutions to new problems and perhaps more robust and better solutions to older problems. And I think what's really important here and what excites me the most is that we have this exhaustive set of sort of machine learning tools available to us so that we can focus more on the developing better algorithms, choosing better algorithms, rather than having to concern ourselves with implementation. So having said all of that, and worked in the industry and tried to apply some of these techniques, probably the biggest challenge that I've faced is really not taking these tools and applying them, but trying to get a solution and making it relevant to the domain experts, which are the earth scientists. I think that's really the challenge, is that we can use data science and other ideas, but at the end of the day, we have to deliver something that our clients are going to understand. So this is my first time at SciPy, and I've really enjoyed it. It's been really great. And I think in particular, it sort of changed the perspective on how I'm sort of looking at this problem. So I've sort of adapted my problem statement a little bit. Really what I want to do is to use the data science, but the real importance here is to communicate properly with the earth scientists. And that's what I want to talk to you today, at least an attempt that we made to do that in this problem. In order for me to communicate to you, I have to basically give you an overview of the inputs to the problem, the basic setup to the problem. I'm going to talk to you a little bit about the sort of SciPy Python ecology that you can use to process it and deal with it. I'm going to show you how to visualize earthquake data using matplotlib. Then we're going to move on to some ideas of basically earthquake learning with kernels, like how we're going to use some of these machine learning algorithms to do this classification. This is fairly general. This is just classification on the surface of a sphere. But in order to make that connection, in order to get that meaningful result that we can then communicate to people, we're going to have to delve into the internals of these algorithms a little bit in order to really understand the physics of the problem. So I'm going to talk a little bit about physics. All of the results I'm going to present are going to be with a comparison to the existing state-of-the-art, which is an algorithm from the USGS called HASH. So this is a sort of a least squares earthquake classifying code. And if you download the HASH software, and I'll provide the URL to it, it comes with a demo data set, Northridge data set. And for the sake of reproducibility, all of the software that I've made available on the GitHub, if you download this demo data set, you can then run and reproduce all of the figures in the talk today. And then we'll just wrap up with some conclusions. So basic overview of the SciPy Python ecology that you're going to want to work with for dealing with these problems. The GitHub made available the basic code. You can go to the USGS website and download HASH. That'll give you the demo data sets. I didn't really want to be responsible for shipping their data. Visualization is done with a matplotlib plugin called MPL StereoNet. I'd just like to have a shout out to the HashPy project, and that was where I got the idea of actually visualizing the data this way. If you are interested in accessing seismic data for yourself, you can make requests to Iris. And of course, scikit-learn for all of our machine learning needs. And for everything else to do with processing the earthquake data, we're going to take advantage of the OBSPy seismological library. So just to give a basic overview of the problem, why we would want to, like a scenario where we would want to classify an earthquake. So we've shown here, we have an earthquake somewhere in the Solomon Islands, and it's radiated energy out. We have a network of seismometers distributed about the Earth, and I've shown that the sort of northern part of the Australian seismic network. what the energy that gets detected at these sites, I've rendered in the middle of the time series in the middle of the page. And this is data that I've downloaded from IRIS. So this is an observation of this earthquake at the location of the Warramunga array. And this time series data in its own right is actually an interesting area for testing time series analysis and things of that nature. So in terms of understanding how we are going to deliver our results to our domain specialists, we have to understand a little bit about the glyph that I've put in the top right corner of the screen. And a lot of you will be earth scientists and you'll immediately recognize it. But it's actually a very information-rich diagram, and having come from outside of this domain, it's actually sort of a little bit of a curious thing. So imagine that you could transport yourself to the location where the earthquake had happened in the Earth, and you're drawing a sphere around that earthquake. The earthquake is basically a slip of particles along some fault plane, and that's radiating energy in the form of some sort of seismic wave, which is causing displacement. The assigned amplitude of that displacement, so whether the displacement was inward or outward at a particular point on that sphere that we're imagining around the source, is represented by the black and white regions of that diagram. The reason that you might be interested in trying to estimate that diagram is because given a certain orientation of that displacement, there can be a risk of, say, a tsunami being caused, and that might be something from a hazard monitoring perspective we might want to be aware of. Additional information that we can get out of this diagram is that as data scientists, we could look at this and say we've got two classes of data separated by some decision boundary, and these are two intersecting great circles. Because they are two intersecting great circles, this actually also communicates that the mechanical properties, the mechanical process of this earthquake was one where particles had slipped, failed under shear, and slipped along some fault plane, as opposed to cracking. So we've got a tremendous amount of information that we've encoded in the form of this little glyph, and all of our machine learning and classifying algorithms have to be able to deliver results in the form of this beach ball, which coming out of quant finance is kind of far out, actually. I don't know if you guys. So just to have a look at how we're going to visualize the data on the stereo net, imagine we've taken observations whether the displacement was outward or inward at points from our seismic network, and we've migrated that back to the neighborhood of our earthquake. So say the red points were our data, where the observation of displacement outward, and the blue points where our data was the displacement inwards. And I'm going to use the words sort of radiation and displacement interchangeably, and that's just a consequence of having been brought up doing theoretical physics. So as data scientists, it's pretty straightforward. All we need to do if we want to find that decision boundary is simply classify this data. And that's incredibly, it looks a little bit complicated. The data is sort of laid out in a bit of a haphazard fashion. But if we take our support vector machine from scikit-learn, we can find a decision boundary that's going to pretty well separate the two different classes. So we see we've got red points and blue points more or less separated by this classifier. And we could just deliver this as our beach ball and say, job done. We're sort of finished. But what I want to talk a little bit more about is why is it that we would want to use a support vector classifier as opposed to some sort of alternative least squares algorithm? And the reason is if what's happening as we approach the decision boundary is that the amplitude of this radiation pattern is becoming small and then it's changing sign. So the relative signal to noise at and along this decision boundary is becoming high, and the data is going to be more error prone. On the other hand, what's most informative for the shape of that curve on that sphere are actually points that lie along that decision boundary. So the data that's the most error prone is the data that's also the most informative. And so on the right here, I've got a bit of a schematic representation of how a support vector machine works. Instead of trying to somehow minimize the overall rate of misclassification, what the support vector machine does is it basically takes the data in some input space where it's not, in this case, linearly separable, right, because we're on the surface of a sphere. It projects it up into some high dimensional space, and then it tries to estimate some sort of separating margin that would discriminate the different classes of data. Data that lies within the margin can be considered to be ambiguous. We don't necessarily have to insist that we understand the class of every data point. What it learns is a function whose sign is whose sign classifies the data. So if the function's greater than 0, say it's a red point. If it's less than 0, the displacement is inward. And so this particular algorithm is going to be more stable for classifying earthquake data than a least squares algorithm that's not going to deal with very well with sort of misclassification along its decision boundary. So say we would deliver this as our product, what we have to ask ourselves is what have we really learned about the mechanics of the process? We've simply provided a picture of what we think the displacement should look like. If I would fill in the area or color the area within that decision boundary, I would have a beach ball. But we haven't really talked anything about the mechanical process. And in order to do that, we have to delve into a little bit of the physics of the problem and a little bit of the internals of the support vector classifier. So just to give you some insight on how you might want to use and configure these sorts of classification algorithms in Python, I provided a little code snippet, which you may or may not be able to read. But the basic ingredients to this classifier are a kernel. A kernel is what projects us from our input space of our data to the high dimensional space where we're going to do our classification. We're going to need some sort of and the type of kernel that we need is a polykernel in the parlance of a support vector machine, but that's actually a sort of inner product kernel. And that particular kind of kernel is appropriate for classifying on a sphere. So I know some of you might have done machine learning and used radial basis functions, and they wouldn't be appropriate on this domain. We have a degree parameter, which we're setting to 2, and there's actually a physical reason why we're setting that to 2. It's not just because it's bigger than 1 and less than 3, essentially. Ordinarily, all we would need to do is to configure the support vector classifier and then fit it on our training data, which are our observations, and then we can use that to classify what the signed amplitude of the radiation should be everywhere in the space, and we do that with a predict function. But in order to delve into the physics of the problem, we're actually also going to have to carry away these dual coefficients. And that's these dual coefficients we're going to use to try to understand what this radiation pattern means physically. So say we got asked a question, you've classified this earthquake. I've got the red dashed line represents, the output of our classifier. And like a domain expert comes to you and says, well, I think this process ought to be due to some sort of shear failure in particular. What would be the best solution given that model? And I'll talk about how we're going to find that. The genesis of this whole line of thinking actually came from one of my colleagues. We had a problem where we were trying to render in 3 dimensions a series of these beach ball diagrams using Mayavi. And what we realized was that we could render both the processes due to shear and tensile sources using the signed amplitude of these spherical harmonic functions, which we can get from SciPy's spherical harm library. And so the light bulb sort of went on. Now, if we wanted to render in 3 dimensions the glyph that I showed you on the first slide, all I would have to do is to take that example spherical harmonic and generate a rotation to properly orientate it. Okay. So that sort of was an empirical observation, and it seemed to be, functionally useful for, fulfilling our coding requirements. But to really understand why that's the case, we have to sort of delve in a little bit into the theory of seismic sources. And to do that, we've sort of borrowed very heavily on the formalism of Ben Menahem and Singh. And what that does is basically we can understand the shear and tensile sources of the earthquake in terms of some spectral content of these spherical harmonic functions. So basically what we show on the left is a 3D visualization of a signed amplitude, right? It's like a beach ball diagram for the 2 different kinds of processes. And on the right, what we're showing really is if the content of spherical harmonic functions that we would have to add together to generate these figures. What we can take away immediately from this is that the shear source and the tensile source are topologically different. The shear source is an intersection of 2 great circles, and this is not the case for the tensile source. So there's no rotation or smooth deformation that could ever transform one into the other. And this gives us some opportunity to distinguish one from the other, given one event is dominant. The tensile source also has an additional component, which we call a monopole component, and I'll talk about in a bit, that is not present in the shear solution. And what that means is that we also have an opportunity to differentiate an admixture of these two sources, just given the polarity data. So to sort of render a little bit, to give you a kind of a picture of what these spherical harmonic functions look like, I don't want to take too much away from this, but basically this is the signed amplitude. They come in groups. By physical arguments, we're only going to need these monopole and quadrupole terms. We're not going to need the other ones. The kernel parameter degree 2 was what generates the truncation of that problem. So we'll never try to fit anything that has these higher order sort of crazy shapes. And by taking the dual coefficients out of our support vector classifier, what we do is we can express our classifying function, right? The thing for which the zero of that function is our decision boundary. And we can express that in terms of a basis of these spherical harmonic functions. So on the left-hand side, I have a view of the result in what I'd call the input space of the data. So this is defined on the surface of a sphere. On the right-hand side, I'm plotting essentially what I would call the feature space of the data. The spectral content of the solution, essentially these coefficients F, represent an image of what that solution should look like in the higher order space that we're projecting, our support vector machine is projecting into. And that's what connects the dots. So basically what we can show by taking our kernel, our inner product kernel, and doing a kind of multipole expansion is that the amplitude, the radiation pattern that we're trying to classify is a function of these spherical harmonic functions. We have templates for what the earthquake source mechanism should look like in terms of these spherical harmonic functions. And so we're connecting the classifier to what the domain specialist knows using the physics of the problem. So if we wanted to solve our problem of finding the best shear model, given our set of observations, all we got to do is to take our template solution, so we know the spectral content of a shear model in a particular orientation, take our learn solution from the classifier, which we know in terms of a spectrum of these spherical harmonic functions, and find some rotation that would maximize the correlation between the two. This would be difficult if we were to do it in the input domain of the data. So if we would somehow put like a mesh grid around the data, we would have to then generate rotations of this mesh grid. But borrowing a little bit from quantum theory, we realized that we can actually generate rotations actually in the feature space. If we want to generate a rotation in the input space of the data, we can do that by actually acting on the features of the data. And the rotation and so that gives us a rotation matrix, this Figner D. And what that's doing is that's mixing up that spectral content. And if we would then render that, we would see a rotation in the input space. So that matrix there is a 5x5 matrix at our quadrupole term. Our vector is of length 5. So computationally, this is an incredibly efficient way of generating rotations. And we exploit that in optimizing the correlation function here. So we could use this technique in an application where we needed to very quickly, say, classify very large sets of earthquakes. So to have a look at the solutions, the red dashed line is the original learned classified decision boundary. That would be our beach ball. The solid red line is the best shear solution that we've derived by optimizing that correlation function. The green line is the solution that's found by the USGS hash algorithm. Given that this is their demo data for their software, we would expect that their solutions are pretty good, and we see that the solution we come up with is very similar. And just for a reference, I provided the little code snippet, 10 lines of Python that you need in order to do this analysis. So the question is, why would we want to use a support vector classifier when we have a perfectly good algorithm called hash, right? I mean, why would we want to do that? Okay. So the training data set has basically a set of post facto processing that's done to identify errors in the original observations. So stations that were reporting the wrong polarity at different points in time. So suppose we didn't have access to this sort of correction. How would the solutions to the earthquake classifiers change if we wouldn't have this looking forward. So what I've shown on this figure is an observation with a bit. I've labeled it with a here. The dashed lines are the original solutions given that data set. Now, not having the benefit of this station correction, say, we would flip the sign of that bit, right? The green line shows the change in the hash solution, which is very large. But however, because that point is very close to the separating margin of the support vector machine, it really doesn't really care. Like it's happy for that data point to be a little bit ambiguous, right? And so we see that the support for classifying solution is actually robust to that sort of misclassification on its separating margin. Another thing that we can do is that we can actually calculate a correlation function to compare different types of earthquakes. And we can do this without having to presuppose what we thought the source mechanism should be or what we thought the orientation of the fault plane should be. And so to demonstrate this, I've taken a particular earthquake out of the Northridge data set as an example, and I've calculated the correlation coefficient with all of the other sample data. And we see that these earthquake mechanisms are very correlated. The correlation score is very high. And you'd expect that based on the literature that was done by design. As a test, we've taken the reference source and we've rotated it by 90 degrees and calculated the correlation with itself. Correlation is very low, as we'd expect, and it's largely uncorrelated with a similar tensile source. So it is a good discriminator. Using this technique, we do have a good discriminator between shear and tensile sources potentially, and we do have metrics for comparing similarity between sources without having to make prior assumptions. So this is just a visualization of that. On the left, I have the reference solution, and on the right, I have the most and least correlated solutions. And so that's it. So I've talked to you a little bit about an idea for a sort of interdisciplinary approach to an old problem. I showed you how to configure your classifier if you ever wanted to classify things on the surface of a sphere. I talked a lot about translating between the point of view of the machine learning data scientist to something that could be understandable by the earth scientist. I've made comparisons with the hash algorithm. We've talked about stability and robustness and why we might want to use it. And I've shown you that we can derive a metric of similarity, which we can use to discriminate different earthquakes. And of course, the code is up on GitHub, and you can run all of the demos that you saw today. And that's all. Thank you.
Questions?
Yep.
What is the data that you use to compute the kernel? You did it to the inner product between the time domain data?
Yeah, so it essentially takes what we're looking at is these data points here that I've rendered in 3D. It's taking those data points and essentially using it in a product kernel to classify it.
So just like their longitude and latitude?
Yeah, just the longitude, latitude. It's just the first break polarity. Yeah.
But I mean, the ultimate input data is waveform data from various seismometers, stuff like just like the hash algorithm.
Yeah, although, I mean, just to simplify the discussion, I mean, we've just used the Northridge data set that's already giving us data points in terms of longitude, latitude, and polarity. So that's the data set we're training. That's what we're rendering on the sphere. Yeah, that's correct. So we're not trying to estimate amplitudes or doing any of that sort of thing. And I'd argue that we don't really need to do that necessarily. Yep. That was sort of the domain we were working in when we were developing these ideas. And in that domain, you really have large numbers of earthquakes that are coming in, and you don't have the benefit of any sort of post-processing or really cleaning up the data. You just have to try to get a good solution quickly.
So just broad, without a lot of detail, how frequently do you see attention CLVD?
I don't know if I really want to go into that. I don't really want to talk specifically about.
Roughly, never.
I could answer a different question. I could say, would I expect to see a tensile source in a context of, say, a microseismic monitoring application? And the answer to that question would be no, I wouldn't. I would only expect to see shear failure of the rock.
Would you not see the tensile just simply because its magnitude is too low?
That's correct. That would be my opinion, yeah. I mean, I think what we're seeing really is, in terms of microseismicity, is just sheer failure of the stress field that's already sort of baked in the cake, and it's just been perturbed and it's failing.
So all those discrete fracture networks interpreted that's hydraulic fracture, basically.
Well, I mean, if you think about, I mean, trying to view a fractured tip as generating a tensile earthquake, I mean, what's the surface area of that, right? So what's this magnitude moment? Could you expect to observe that on the surface? No, probably not. Yeah, so that's my personal opinion. That's not related to anything else. Yo.
Really quick, so I'm probably wrapping up with all my random things. I maintain industrial and also love you.
Oh, okay, thanks a lot.
Stuff for tokenizing. Can't open it, there's no option to get around it. But
Yeah.
I think what you're doing with taking a full-on SVM model and getting a non-double solution and rotating double solution is really slick. But most of these things solve directly for a non-double solution like hash.
Yeah.
Would you advise if you could take, basically, would you expect a difference in terms of sensitivity if you took a SVM type approach with a kernel that was explicitly non-double coupled, explicitly double coupled, so it had only, basically eliminate the all-fact?
Yeah, I mean, that's sort of the punchline of the talk is that the support vector machine, it doesn't make any assumptions about, a priori assumptions about what the mechanical process ought to be, right? It's just learning, it's just drawing a line, it's making a beach ball. And for me at the time, I was like, great, I'm done, that's awesome, But, if you want to delve into the mechanics, you have to kind of look into the spectrum, and that's sort of what we were trying to get at, is that we can look at the spectrum of the solution that we've learned, and then you can try to make inference based on that. So you can make a test, say, is this what would be the best shear solution? What would be the best tensile solution? And if I had a source that was tensile, is it correlated with what I'm observing now, or can I find some orientation that would correlate it? That's the sort of idea. So I don't want to. I mean, the data science machine learning side of it is really just to let the data drive the problem first, without having to make a priori assumptions, and then second you go in and try to understand the model that way.
Any other questions? All right, thanks very much.
Thank you.